The distributions that we have discussed so far have been based on some ideal scenarios and some ideal assumptions. But the probability density functions for the physical processes that we normally study, they encounter some complications. So first of all, in real life, the PDF is quite likely not one of the ideal distributions we have studied. In fact, the PDF may even be difficult to calculate. Or even worse, it may not even be known. Secondly, the range of variables that we encounter. That is never minus infinity to plus infinity. This may be limited by physics. So, for example, conservation of energy, or there may be a limitation of the apparatus. So, for example, a radio telescope only works in a certain range of frequencies. So, in such cases, we must use conditional PDF. So something like the probability density of x given x lies between the range x minimum and x maximum. As a third point, the physical PDF may get modified by the detector response. In such cases, this response must be convoluted with the physical PDF to obtain the PDF which is actually sampled. So, if we consider an example such as beta decay, and we want to measure, let's say, the energy of the electron. Now, this may be distributed according to a PDF which is given by the theory of weak interactions. But we measure this energy with some apparatus which has a certain resolution. So, instead of this EI or E1, we record some deviation from it, E1 plus delta, let's say. And this delta is distributed according to the resolution function of the apparatus. Now, this resolution function in itself may be a PDF. So let's call it F2 for delta. So now the question becomes, what is the PDF, which we may denote as F of E, of the quantity we record? So this F of E is called the Fourier convolution of F1 and F2. Now, we'll work with the assumption that E1 and delta are independent. Now, this is reasonable since E1 comes from a physical process and delta is something extra added by the apparatus. It has nothing to do with the decay itself. So then the joint PDF this can be written as F12 for E and delta is a product of F1 or E1 times F2 for delta. If we compute the CDF, the cumulative distribution function for E, then F of E is given by this integral where we can basically break this integration into two parts. The E1, let's say, goes from minus infinity to plus infinity. While delta from minus infinity to E minus E1. Now, this in itself, this integral over delta, gives a cumulative distribution function for F2 up to E minus E1. So what we have now is F of E. So an integration from minus infinity to plus infinity over E1. We have F1 of E1 times capital F2 of E minus E1. Alternatively, this can also be an integral from minus infinity to plus infinity, where we are integrating over delta. We have F2 of delta and a cumulative distribution function capital F1 for E minus delta. Based on this, we can calculate the PDF simply as a derivative of the CDF. So in both cases, the derivative basically acts on the CDF in the integrand, so turning that into a PDF itself as well. And this is nothing but convolution of the two PDFs. Now, something which comes out to be pretty useful in evaluating convolutions is the characteristic function. So let's say we have phi of t using a subscript f, we rewrite this PDF in terms of the convolution. So we leave the exponential intact. Now we can rewrite E as the sum of E1 plus E minus E1. And this allows us to rewrite the above integral as e to the power I t E1 F1 E1 and e to the power I t E minus E1 F2 E minus E1, and we have the integration measure in terms of dE1 and dE. And from here we can identify two distinct characteristic functions and rewrite the full thing as a product of the two. So this is a product of phi f1t and phi f2t. So assuming independent random variables, the characteristic function of a convolution is just the product of the individual characteristic functions. Now, in the above example, we have assumed a detector response independent of what is being measured. Now, in practice, the distortion of the input signal usually depends on the signal itself. So, distortion of signal is maybe some function of the signal. This can happen in two ways. So first is the detection efficiency. The chance of detecting an event with our apparatus may depend on the properties of the event itself. So let's say we want to measure the frequency distribution of electromagnetic radiation incident on Earth. But some of this radiation is absorbed by the atmosphere. So now, if Fx denotes the PDF for frequency x of incident radiation, and Ex is the probability that a photon of frequency x incident on Earth will be detected. Both of these, F and E, may depend on other parameters. For example, the direction of space in which we'll look. So ultimately, the PDF of frequency of the photons that is detected that would be given by function g of x. Where y easily refers to the other parameters. The second thing is the resolution. So let's say the detector records a frequency x prime when the incident photon has frequency x. And let's say r x comma x prime is the PDF for the above. Then g of x prime will be a product of r and f. We integrate over all x's. Now if r is just a function of x minus x prime, we get the simple convolution under the above. And the resolution effects can lead to values of x prime which lie outside the physical range. For example, an energy of a particle which is larger than the maximum energy allowed by the energy conservation. So, now if the resolution function is Gaussian, and if the physical PDF fx is also Gaussian, then through the reproductive property of the Gaussian it can be shown, or by evaluating the convolution using the characteristic functions, we can show that the PDF for x prime is also normal. So what we may get is gx prime equals and this may turn out to be sigma square and tau square are the respective variances of f and r. So next, let us discuss a very important theorem, which can also be called the central theorem of statistics. It's known as the central limit theorem. So given n independent variables, let's call them xi, distributed according to PDFs fi, having mean mu I and variances sigma I square. The theorem states that for the sum of the xi, the expectation or the mean is sum over the mu i's, the variance sum over sigma I square, and the PDF itself approaches the normal PDF described as the parameters the sum over mu I and sum over sigma I square as n tends to infinity. Or in other words, limit as n tends to infinity, or f of s is n plus mu I and a similar summation over sigma I square, where s is the sum over xi's. It must be emphasized that the mean and variance must exist. Now, the proof of the central limit theorem in the general case is a bit involved, so we'll only demonstrate it for a restricted case where all PDFs are same, so all fi f. Without loss of generality, we set mu equals to 0, and sigma square is simply the expectation of the second moment. Additionally, we assume that not only are the mean and variance of f finite, but also the expectations of the higher powers of x are finite, so that we can expand the characteristic function in a power series. If we define a variable u as x by sigma times square root of n, and the PDF for u has variance 1 by n. And the characteristic function can be expanded in a series like this. Now we recall that the characteristic function of a sum of independent random variables is the product of the individual characteristic functions. So characteristic function for SU, which is the sum over UIs, can be given as this quantity in the limit of n going to infinity is nothing but the exponential. But this characteristic function is nothing but the characteristic function of the standard normal. Since we can show this relation between S of u and original S, the PDF for S is simply the normal PDF, n with S as the random variable, mean n mu, and variance n sigma square. Now, corollary of the central limit theorem is that under the conditions of the central limit theorem, the PDF of S by n approaches the normal PDF as n goes to infinity. In the case that all Fi are the same, then the limit basically becomes the central limit theorem shows why the Gaussian PDF is so important. Most of what we measure in day-to-day experiments is in fact the sum of many random variables. For example, you measure the length of a table with a ruler. Now, the measured length depends on a lot of small effects such as optical parallax, calibration of the ruler, the temperature, the shaking of our hand, etc. A digital meter, similarly, has electronic noise at various places in the circuitry. So what we measure is not only what we want to measure, but added to it a large number of small contributions. If this number of small contributions is large, then the central limit theorem tells us that the total sum is Gaussian distributed. And this is often the case, and this is the reason resolution functions are usually Gaussian. But if there are only a few contributions, or if a few of the contributions are much larger than the rest, then the central limit theorem is not applicable and the sum is not necessarily Gaussian. The central limit theorem also shows the effect of repeated measurements of a quantity. Let's say we measure the length of a table with a ruler. Now, the variance of the PDF for one measurement is sigma square. The variance of the PDF for an average of n measurements is sigma square by n. Thus, the standard deviation is reduced by a factor of root n. If a random variable is the product of many factors, then its logarithm is a sum of equally many terms. Assuming that the central limit theorem holds for these terms, then the random variable is asymptotically distributed as the log normal distribution.